Hello, everyone, and welcome to Addressing and Routing. This is going to be episode 4 of this networking series that we're doing on this channel. If you have not taken a peek through the first 3 episodes that we have already done, there is a playlist in the description. I do recommend watching these in order. That way, you have the same information that I'm assuming you guys have already going through this. We have some definitions that are already defined and a few functions that have already been defined in those past episodes that will help learn a little bit better as we move on. This episode will be significantly longer than the last few. This is where a lot of networking happens. So this is really the core, the kind of backbone to transit and networking and communication. So grab a cup of coffee, grab a glass of water, and, if you need to take this episode in 2 parts, go right ahead. But let's just dive right on in with the networking layer. Again, this is OSI and 5-layer model layer 3. In the TCP/IP model, this is layer 2. Let's start off with a general question here. What is an IP address? Well, it stands for Internet Protocol Address. It's a unique logical address that identifies a device on the network. Every device has to have a different one, or you're going to have some conflicts. Multiple devices on the same IP address don't tend to work too well. One of them gets kicked off because the other one takes priority, the other one exists and pops up, so you will have data loss. It has to be unique in order for data to flow correctly. And it is assigned to each device on a network. Again, any kind of a host node, any kind of like a switch, server, computer, router, anything like that, printers. Well, didn't really answer the question. What is an IP address? Well, it might look like 192.168.1.1, or it may look like this. That first address is an Internet Protocol version 4 number, which is a 32-bit numeric IP address. The second option here is Internet Protocol version 6, which is a 128-bit alphanumeric. They released that IPv6 system several years ago. Still not taken hold of the local area network world. It is becoming more popular in the wide area network, the internet service provider point of view. Because there is an IPv4 address shortage in the public space. In this series here, we're going to be primarily diving into IPv4 addresses since they are still more commonly used. Let's take a peek at an IPv4 address. Well, it's made up of 4 octets. Again, an octet would be 8 bits of data. So there's each number in there is 8 actual bits of data. Octet.octet.octet.octet. They range from all zeros to all 255s. The way computers function, 0 is the starting number and not 1. So there's technically 256 options in each octet. There's a couple rules to IP addresses. Some addresses are not usable for hosts, or just not usable in general. Some addresses are reserved with the Internet Numbers Authority. We're going to take a little peek at subnetting. This is where stuff might get a little bit complicated here. We're going to do a little bit of IP conversions to binary here, just so you have some information here a little bit later on. If you do need to skip through some of that, if you don't feel the knowledge is applicable, obviously, just skip ahead a couple minutes, see where we're at. But subnetting is a logical subdivision of a network. Again, logical is virtual. It's a virtual interaction. There's nothing physical functioning at this layer. Subnetting is essentially a chunk of network address space with a defined size. Subnet size is defined with a subnet mask, which in binary marks all host available addresses with a 1. I apologize, that's a typo. It marks all unavailable addresses with a 1 and all available addresses with a 0. There we go, there's the fix. The smaller the subnet mask, the larger the IP subnet space. All networks must have a broadcast address and a network address. A subnet is still a network, it's just a smaller network, usually attached to a bigger network. A subnet mask may look like one of the following: 255.255.255.0. Again, we discussed there's 256 options, everything starts at 0. That size has 256 addresses. A subnet mask such as 255.255.255.252 has 3 usable addresses. Again, everything that is marked with a 1 is unusable. Everything that's marked with a 0 or those last 3 are usable. 255.0.0.0 has 16.7 million addresses in that subnet size. Slash notation is commonly used in the display for a subnet on a network size. This representation sums up all the 1s in a 32-bit subnet mask and appends them with a slash to a network address, such as 192.168.1.0/24. Here we're going to get into those conversions, so if you don't feel the need to know this, skip ahead a little bit, but we'll try to go through it a little bit quickly. Converting to slash notation. For a mask such as 255.0.0.0, all the bits in the first octet are 1 because we're at the max size on that first octet, but all the others are set to 0. You write out each bit. Again, each section is an octet, which means that there's 8 binary bits, 8 1s or 0s in there. So written out, it would look like first octet's all 1s, followed by all 0s on the remaining 3 octets. If you sum up all the 1s that are written out, we get 8. The subnet mask 255.0.0.0 has a slash notation of /8. Well, that's fine and good, but what happens when a subnet doesn't end in a 255 or a 0? Well, each spot, each value in that octet, each bit, has a specific value assigned. Those values are as follows. Starting from the right, it's a 1, it doubles. Again, starting on the left, it's 128, and it cuts in half. This is the same conversion method for converting a standard IP address. Does not only apply to subnet masks, but it does apply to any IP address whatsoever. We're going to add or remove the appropriate value for each 1 in the octet of the subnet. So we're going to take a little example of this here. For a mask such as 255, 255, 255, 252, most of the bits are 1s except the last 2. When each bit's written out, first 3 octets, we already know they're all 1s based on those 255s. At the end, that last octet is not all 1s, but if we look at these places here, we're going to slide back to this slide here. We know that the 128 is going to go into 252 plus 64 plus 32 plus 16 plus 8 plus 4. When you sum all those together, you'll see it does equal 252. So we can take the 252, we can subtract each place starting from the left. Each one that's applicable is going to be a 1. Each one that's not applicable or cannot subtract from because it's too big, it'll give you a negative number. That's going to be marked as a 0 bit. Written out, we know that those last ones, the 1 space on the right and then the 2 space second to the right, that's what obviously 5 minus the sum of those, which is 3, is 252. That subnet mask obviously is going to be a, if we sum up all those 1s, it's a /30 for the mask 255.255.252. This is a super common subnet mask to see on a wide area network or a public public space, an internet service provider is likely going to hand you a /30 block if you have a static IP address with them. Well, let's do the opposite. Let's convert from slash notation. This one's a little bit easier. Well, we know it's a /29 network, so let's write out 29 ones. We're going to separate each in the chunks of 8 for each octet, and, well, we just do the math. So, again, we know that that far left space in that 4th octet is 128, so we just need to add 128 plus 64 plus 32 plus 16, plus 8, and, well, we get 248. So, each octet that is all ones we know is 255. For each octet with a mix, lower than 255, well, we're going to add the appropriate number. We're going to find /29 network has a mask of 255, 255, 255, 248. Again, starting from the right of the octet, it's 1, 2, 4, 8, 16, 32, 64, and 128. Starting from the left, 128, 64, 32, 16, 8420. The same conversion will apply for standard IP addresses. You will not always have ones in order to convert a standard IP address. You might have some bits that are 1100, 101. It's going to be a mix, but the same method, same conversion method does apply. It's just a little bit trickier because you will have to move down and make sure you take up every option in that octet space. Well, out of the math section here, out of the conversion section, we're going to take a look at the actual size of a network. Well, the largest the internet goes is a 0000/0. That's the entire internet, and that contains, 4.3 billion IP addresses. The smallest it goes is a 255.255.255.255/32, and it is one address. Subnet masks can range from a /0 to a /32. You will never see a /0 unless you're referring to the internet as a whole. A 32, again, applies to one singular address. A 31 is a bit special. It doesn't really exist because it's two hosts with all either ones or zeros in the IP address, which means it's either 0000 or it's 255.255.255.255, which aren't usable addresses. So this means that two devices could technically communicate on a /31, but they're blocked off from the entirety of the rest of the internet. Could be used for a point-to-point link. There wouldn't really be management access into that, but in theory, it could be used for a point-to-point link. It is extremely rare that you would ever see a 31. You would usually do something like a /30 network with two devices attached. That way, at least, you can have some management access into those devices. Well, again, how do we determine the real size? Well, each one in a mask, each one in those octet data, breaks the size in half. A 192.168.0.0/23 has 512 addresses. Again, if we add a 1 to that, make it a /24 network on the 192.168.0.0/24, it has 256 addresses. With each break, we lose 2 usable addresses for them to become the new network address and the new broadcast address. Again, every network needs a network address. Every network needs a broadcast address. We lose those 2 addresses when we break it in half. Again, on a /23, we already have that 0 address is assigned as the network address. The 1.255 address would be assigned as a broadcast address. If we cut it in half, we're going to lose 1 additional usable IP from each new subnet to fill in for either the network or the broadcast address on those networks, those new subnetted networks. So we lose 2 total available addresses when we cut the network in half. Let's talk about unusable addresses. We already discussed that some are unusable and some are reserved, so let's chat through those. Well, the first one is the broadcast address, which we just mentioned. It's the end address in a network. 192.168.1.255 in a /24 network. That 255 address is unusable as it is a broadcast address. Network addresses are also unusable. In a 10.10.10.252/32, that 252 is the start of a network. Again, 255 would be the broadcast in this case. 253 and 254 would be the two usable addresses on the /32 network. Addresses ending in a 0, well, they're often network addresses, as in the example above that broadcast address. The network address for that network would end in a 0. They're not always network addresses if the network size is larger than a /24. Again, larger would be a smaller slash notation. So a /23, there would be an address ending in a .0 that would not be a network address, but a .0 address cannot be assigned to a host. Well, let's talk about those reserved addresses. The Internet Numbers Authority, actually, it stands for IANA. It's the Internet Address Numbers Authority. They define some address space as being reserved for certain cases. One of those networks is 0000/8. It's anything starting in a 0, refers to this local network. It just means that this local network has access. Next is 10.0.0.0/8. Anything beginning in a 10 is reserved for internal use only. It means it can be on a local area network. It does not exist on the public area network side. 172.12.0.0. It should be anything starting in 172.12 through 172.29 is an internal only address again. Third internal address range is 192.168/16. Don't know why I didn't finish out that typo there, but it's anything starting 192.168 through, I believe, 169. Another one is 127.0.0.0/8. So anything starting in 127 is a loopback address. It means that it's local to that host. You might see this with an internal, like, listening web server or an internal connection between processes on a computer. You might utilize a 127 address in order for the computer to talk to itself via a network connection. 100.64.0.0/10 is reserved for carrier grade NAT or LSA. We'll talk a little bit about NAT later on, but CGNAT is just an enterprise version of normal NAT. It's public address space reserved. 169.254.0.0/16 is reserved for link local. This is, or a PIPA, which stands for Automatic Private IP Address. This is typically what happens if you plug a computer into a network and there's no DHCP server handing out IP addresses. Your computer will take on an IP address starting in 169.254. That means that you could still talk to other devices on that network with 192 or with 169.254 addresses, but you don't really have a default gateway. You don't have a way to send out of that network, but you could talk to other devices on that network. The final set of reserved addresses is a 240.0.0.0/4. takes up everything from 240 to 254. Reserved for experimental / future use, but we've never seen future use of this section. But it is reserved. It is blacklisted from public IP space. It is reserved. Well, let's take a peek at the Internet Protocol packet, the Layer 3 data packet. This one we'll see is a bit bigger than a frame, but this data is the payload in an Ethernet frame, a Layer 2 frame. The payload section is all of this data here. Well, we're going to start off with the IP version, defining if it's, version 4, version 6. Helen, which stands for header length, gives the defined length of the header. That way we know where the data actually begins. DSCP is a quality of service tag. We're going to look at length tag, identification tags, miscellaneous flags, any kind of offset, time till live, the protocol being used, a checksum for the data, the source IP address, the destination IP address, options, padding, and data. Let's take a peek at each of these items in a little bit more depth. Starting off with the version, obviously the Internet Protocol version. Helen, it's the header bit length, says when the data starts. DSCP is quality of service or a data type flag. Length is the absolute total packet length. Identification is a identifier for packet fragments. If a packet has to be broken up and the data has to be sent over multiple packets, this is an identification for reassembly on the other side. Flags communicates the fragment state. Offset, again, is the fragment offset of the data bytes. It's all about if the data has to get broken down into smaller chunks as it goes across. It's about reassembly, all those flags right there. TTL is time till live. The maximum time a packet is live. Protocol. This might be TCP, UDP, etc., something like that. ICMP, IGMP. Checksum. Checks for header integrity. Make sure all the header data exists. Source IP address is the sender's IP address, destination recipient's IP address. We have to know both so that we can get response messages back and forth. Options, this is an optional flag piece of data. Usually it's used for security info, maybe timestamps for packets, make sure a packet hasn't aged in transit, or is being maybe tampered with. It is an optional flag though, so only used in certain cases. Padding is added to ensure the header is a multiple of 32 bytes. The IP header at this layer has to be a multiple of 32 bytes. Data is the layer 4 data segment, the actual data inside the packet at layer 4. We're going to go into NAT a little bit. NAT stands for Network Address Translation. Oftentimes it's putting a private IP network behind a public address. It's one of the most frequent use cases. Might be used for hosting a server as well. The most common case you'll see is just putting a private IP network behind one public address. NAT's job is to rewrite an address on a packet to a different address. It's typically performed by a network router. Well, let's say we have a packet headed to the global internet with a source of 192.168.0.10 and a destination of dns.google 8.8.8.8. Well, the NAT device would take that packet, rewrite the source to the public address, because 192.168.0.10, again, as we look through, it's a reserved address for internal use only. If Google were to receive a request from that address, it could not send response traffic back to you. It could not give you an answer to your question. If the packet didn't have a public address, there's no way to receive a return packet. It's going to get dropped because 192.168.0.10 does not exist on the public-facing internet. NAT device shows a public IP on. in its place, it goes out. Google knows how to send it back to you because you have a public address on there. Some other uses for NAT is, again, with port forwarding. If an incoming packet's designed to go to a host behind a NAT device with a private IP address, the NAT device can rewrite the destination address of the incoming packet to that of the true destination node. You have a packet hit your NAT device, and your NAT device knows that, hey, this port, this info should be forwarded to 192.168.0.10. It rewrites the destination MAC, and it sends the packet on through that server, that public-facing device, or that public-facing port for port forwarding is going to receive that packet now, and it's going to send it back up to that NAT device, which is going to do the converse then, and then throw the public IP address back on it as it goes out. Well, time to discuss some routing. Well, how do networks communicate with each other? Networks use routes in order to get to other networks. Routers are typically connected to 2 or more networks. Most frequently, you'll see a LAN side and a WAN side. Enterprise, bigger side things, you might see more WAN networks connected. You might have a lot of LAN networks connected as well behind maybe even one WAN network. In the public-facing internet, you might have several WAN networks connected and no LAN networks connected. But at the end of the day, it's typically 2 or more networks connected to a router. There's 2 primary routing types, static and dynamic. Static routes are designed for networks that you know exist in a certain fixed location. Dynamic routes are for networks that you might not know the location for, or they might move around. Usually like a public network where IP space is kind of always changing and you don't actually really have a fixed map for where networks live, or potentially large campus networks where everything might be changing a little bit and you don't want to have to go change static routes on a whole bunch of different devices. Campus networks might utilize dynamic routes because they're just so big that it's more efficient. Yeah, it's a weird slide. All right, let's take a look at a basic route. Well, if we were to route 192.168.0.0 with a mask of 255.255.255.0 through 10.10.10.1 with a metric of 2, what does that even mean? Well, this sends any traffic looking for any device on 192.168.0.0/24 to 10.10.10.1. The goal for this route is 10.10.10.1 knows where 192.168.0.0 lives. The metric is the actual priority of this route versus other routes. You can have multiple routes on the same router, and the metric actually defines the priority of this route versus a different route. The higher the metric, the higher the priority. The gateway 10.10.10.1 must be on the same network as the router. The gateway device has to be on the same network that you're looking for. The router must have direct network access on any of the attached networks to that gateway host that we're looking for, in this case 10.10.10.1. Another feature in routing is what's called a route of last resort. Often there's a last resort route which sends all unknown traffic to another router who may know the location of the destination network. Usually, if this is just a little home internet or small business internet, this is all you need. What it does is it routes everything. Again, 0000 with a mask 000 is all internet. We're going to route all internet through 10.10.10.1 with a super low metric, meaning anything that has a slightly better idea of what's going on will take priority. If another route exists with a higher metric, the traffic will use that route, but otherwise, it will send any unknown destination out to 10.10.10.1. Routes that are manually added to a router are called static routes. Dynamic routes uses standard protocols, often OSPF, EGIRP, RIP, or BGP. We're not going to go into details on these, but these are general protocols for dynamic routing. But it uses these protocols to get route information from any other routers that are on connected networks. This allows a router to have additional knowledge of what might be behind it in order to properly route traffic to the destination. Essentially, a router would go up, grab route tables from routers that are above it, which would grab route tables from routers that are above it, which would grab route tables from routers that are above it. They would eventually trickle back down, and it would build a massive list of routes known by surrounding routers. Now you know that, hey, router A has access to this network or has a route to that network. Router A might not have the direct route, but we send the data up to router A sends it up to router AA, sends it up to router Charlie, whatever, and it goes all around, but a router A we know has a route based on that dynamic routing protocol. It's just a massive accumulative list that refreshes, kind of constantly is updating with each other in order to populate routes of surrounding routers. That takes us to the end of our layer 3 episode here. Again, I know that there's a lot in this episode, significantly longer, probably far more complicated data in here, so I do recommend, if there's any questions, there is a Discord server in the description, and feel free to leave comments below on this data, and I will see you tomorrow with ports and protocols.